Right. Let us now begin once again to our next module, that is on finite queue space and queuing cost models. Now, the finite queue space and queuing cost models, these are very important topics, particularly in the context of queuing theory. Initially, let us look at what really happens at finite queue space. Please remember that all those things that we have said about MM1 and MMS system, really when we talk about MM1, really speaking, this MM1 was something like MM1 FCFS infinity infinity. What are those last two infinities mean? The last two infinities are meaning that there is an infinite queue space and there is an infinite input or calling population. But what happens if they are really not infinite? See, all these simple formula that we derive for our MM1 systems, obviously they hold true for exponential or Poisson distributions, that is Markov processes. Also the queue space should be infinite and calling population is infinite. What happens if input space is not infinite? You recall we have discussed about a particular thing called balking, right. What is really balking? Balking means that not joining queue after arriving. Not joining queue after arriving. The customer has come, but it did not join the queue because the maybe the queue is long, or maybe there is no place really to wait. Particularly in highways, suppose there are something like a petrol pump, and in that petrol pump there is not enough space that is available, right. So, this is here is a problem, only one pump is available. Cars, that means it is a single server, cars wanting gas arrive as per the Poisson process at 20 per hour, but only 4 cars can be in the pump including the queue. There is no other space, and you just cannot wait on the highway, right. You just cannot park your car on the highway outside the pump, right. So, you have to go away, you have to wait for the next pump. That is what really happens to the customers in the next pump. That is not what we really are interested here. We are interested in what is happening in this particular pump. So, the arrival process does not remain exactly Poisson. Why? Because the car has come, but it has balked. It did not join by seeing the length of the queue. So, what exactly should be there? In fact, I know sometimes there is another kind of balking. There are two kinds of balking that is happening here. First of all, if there is the entire queue space is full, then also the people go away. But what really happens? Let us look at this. See, this is the pump, this is the highway, here is the pump, and here is one car that is waiting, right. Now, you are coming from here. As you come here, you think, look here, there is one car already there. Should I join, or should I go ahead and go to the next pump which I might get free? So, you see, even when there is maybe only one car which is getting maybe gas, you may still think, let me not join. So, there is a chance of not joining even if there is one car, obviously, and if there are two cars, already one car is getting fuel, the other is waiting, then you may think, oh, I have to wait long time, right. So, this chance of balking goes up. So, that is what, look at the problem. If there are n cars in the station, probability that an arriving car will balk is n by 4, right. So, n equal to 1, 2, 3, 4, right. That means, when there is only one car in the system, the 25% cars are going away. When there are two cars in the system, 50% of the cars are going away. When there are three cars in the system, 75% cars are going away, and when there are four cars in the system, all cars are going away. Why? Because there is no place to wait. So, really speaking, it is a finite queue space model, because at no point of time the pump will hold more than 4 cars, right, they will be going away. So, all the formula that we have derived earlier, they are not applicable. We have to redo the whole problem from the birth and death process, draw the rate diagram and move from there, right. So, how that rate diagram should look like, right, rate diagram. In this case, the rate diagram should be, first of all we have to know how many states. How many states are there? There are only 5 states, that is 0, 1, 2, 3 and 4, right. So, from the first 0 state, one car can arrive, from 1 another car can arrive, another car can arrive, and then another car can arrive, and if there are service, then all these cars will be going away. So, you see, that is the kind of rate diagram that we can look into. So, let us look at the rate diagram that we have here. In this rate diagram, see, there are, first of all, there are 5 states, n equal to 0, n equal to 1, n equal to 2, n equal to 3 and n equal to 4, right. And what are the values of lambdas and mu's? Lambda 0 equal to 20, lambda 1 15, lambda 2 10 and lambda 3 5, and mu's are all 20. But why are lambda values reducing? Look at this balking effect. The probability that an arriving car will balk is n by 4. So, when there are 0 cars in the system, entire set of cars are coming, that is at 20 per hour. But when n equal to 1, that means there are 1 car waiting, then 25% cars are going away, that is n by 4, in this case 1 by 4. So, 1 by 4 of 20 is 5. So, 5 cars go away, that means 15 cars will really join, alright, and thereafter 10 and finally 5 and then 0, that means there is no such system beyond this. So, in this, let us look at lambda 0 equal to 20, lambda 1 equal to 15, lambda 2 equal to 10 and lambda 3 equal to 5. But mu's are all 20, so there is no need to differentiate them. Right. So, once we have this particular rate diagram, we know we have to say, and please remember, the rate diagram really depicts the steady state situation. So, if this is a steady state situation, how do I get the probabilities? You see that what are some system probabilities? The probabilities are, there are how many different probabilities can you think of for this particular system? There will be only 5. What are they? P0, P1, P2, P3 and P4. That means probability of 0 persons in the system, probability of 1, probability of 2, probability of 3, probability of 4. And how the equilibrium will be obtained? Already we know that in will be at every node in equal to out. So, at node 0, what happens at node 0? Let us see. At node 0, how much is in? How much is in? 20 P1. How much is out? 20 P0. Alright. So, because both the rates are 20, so that means there is an equilibrium, and this will give what? P1 equal to P0. So, we could get one relation very easily by looking at the rate diagram. What happens at node 1? How much is in? How much is in is node 1 20 P2, 20 P2 and 20 P0. And how much is out? Out is 20 P1, right, and 15 P1. All right. So, that is equal to 35 P1. So, like this, if you do all these calculations, you see all these node balance start to be obtained at different nodes, right, and you can find at node 0 20 P1 equal to 20 P0, at node 1 20 P0 20 P0. So, this is 20 P0 that is in, and 20 P2 that is in, equal to 35 P1. Why 35? Because 15 and 20 and into P1. So, I hope you can do all these node balances. Let us see one more, that is at node 4. At node 4, what really happens? 5 P3 equal to 20 P4, right, 5 P3 because 5 P3 equal to 20 P4. So, we get all these equations, and we should also remember that total process is P0 plus P1 plus P2 plus P3 plus P4 equal to 1. Now, how do we find out? So, we get so many equations, 1, 2, 3, 4, 5, 6 equations, and how many unknowns? 5. See, there are 5 equations and we have got 6 equations. That means one of the equation must be redundant. It is also interesting fact here that one equation is redundant. So, you cannot use all the 6 equations, you have to use only 5 equations. But you must remember, those 5 equations, whatever they are, the last equation has to be used, right. That means we have to use the last equation, and we have to use the another 4 equations out of these. So, let us see that and try to calculate and find out what should be the value of the probabilities. So, these are the equations. P1 equal to 20 P0. So, from here we can find out P1 equal to P0, one result. Second, 20 P0 plus 20 P2 equal to 35 P1. Is it all right? So, this will give 20 P2 equal to 35 P1 minus 20 P0. But look at one, P1 equal to P0. So, 35 P1 is nothing but 35 P0. So, this may be written as 15 P0, right. So, this will give P2 equal to 15 by 20 P0 or P2 equal to 3 by 4 P0, right. So, this may be our second equation. Then, and the third equation we have got is 15 P1 plus 20 P3 equal to 30 P2, right. 15 P1 plus 20 P3 equal to 30 P2. So, here we can write 20 P3 equal to 30 P2 minus 15 P1, but 30 P2 3 by 4 into P0, so equal to 90 by 4, right, equal to 90 by 4 or 45 by 2 P2 minus 50, sorry, P0 minus P1 is P0, 15 P0. So, this will give P3 equal to, so this will be 15 by 2, so 15 by 40 P0, right. And finally, 5 P3 that is P3 equal to 3 by 8 P0, and finally 5 P3 equal to 20 P4, where we get P4 equal to 5 by 20 P3 equal to 5 into 3 by 20 into 8 P0. So, this will be 4. So, P4 equal to 3 by 32 P0. Let us look whether they are true or not. See, this is what we have got solving P1 equal to P0, and then P2 equal to 3 by 4 P0, and then your P3 equal to 3 by 8 P0, and P4 equal to 3 by 32 P0. So, we got all the correct results. So, look at the calculations once again. See, therefore, we know P0 plus P1 plus P2 plus P3 plus P4 equal to 1, right. So, P0 plus P0, put all these results, P0 plus P0 plus 3 by 4 P0 plus 3 by 8 P0 plus 3 by 32 P0 equal to 1. So, if you add all of these, so here you will get 32, here you will get 32, 32, 64 plus 24, 88 plus 12, that is 100 plus 3. So, 103 P0 by 32 equal to 1. So, this will give, what is the value of P0? 32 by 103. What is the value of P1? 32 by 103. What is the value of P2? P2 will be 3 by 4 P0. So, it will be 24 by 103. What will be the value of P3? 3 by 8. So, 8 is 12 by 103, and finally P4 3 by 32 will be 3 by 103. So, you see, looks a little difficult, but not that difficult really. You have to really write down the rate equations, obtain that equations by in equal to out, and if you solve those equations, which are nothing but some simple simultaneous equations, and if you solve, you can actually obtain all the probability values. So, once the probability values are obtained, now you can do the rest from the first principles. What are they? You see, already we have found out all the probabilities. Now, what is L? L is sum over NPN n equal to 0 to 4, because in this case only up to 4, right. So, that means 0 P0 plus 1 P1 plus 2 P2 plus 3 P3 plus 4 P4, right. So, if you add them up all, then you get 128 by 103. So, that is equal to L. And then however, we also have to remember that calculation of lambda, that is because you see Little's formula, the lambda that they use is not really lambda, but it required to put what is known as lambda bar. So, what is lambda bar? We have to really compute, that is 20 P0 plus 15 P1 plus 10 P2 plus 5 P3 plus 0 P4. Why? Because at different levels the lambdas are different. So, you have to find out the weighted average for the lambda values also. So, by so doing we have found the lambda bar equal to 1420 by 103. So, these two results will give W equal to L by lambda bar equal to ratio of the two, which is 128 by 1420, right. So, you can find out the waiting time in this manner. So, look at the slide, we get waiting time W L by lambda bar is 128 by 1420 is 0.090 hours, right. So, that is how we solve what is known as finite queue space models. Now, let us look at another problem quickly and try to understand this problem a little further. In this case, there are two agents book airline reservations using two phones, right. In addition, a caller can be put on hold. If all three lines are busy, the customers balk. Poisson arrival is 1 per minute and exponential service time is 0.5 minutes, that means 2 per hour. So, find probabilities for a caller gets to talk immediately, caller will be put on hold and caller gets a busy signal. So, what is happening? There are two phones, right. There are two phones, a person, but there is a single line, and a call comes. If only one call comes, then any one of the phones will be available. If two people are calling, then two phones will be called, and if another person called, then it can be used as a hold facility, right, up to 3. But what happens if another person calls? Then nothing is possible, the person has to go away. That means, the system state can be only up to that two people are busy, they could be on the call, and the third person could be put on hold. So, that is all, nothing else. So, look how many states in this case, look at the red diagram. The red diagram will therefore show that there will be 0, 1, 2 and 3, right. There will be only 4 different states, and out of those 4 different states, what are the lambdas and mu values? The arrivals could be 1 for each case, but mu values, if there is a state only up to 1, then mu value is 2. Why mu value is 2? Because service time is 0.5 minutes, right. So, that means it will be 2 per minute, but when more than one, because there are two phones, at that time the service time could be 4, is it not, because service time will increase under those situations. So, what happens? Why no arrival beyond n equal to 3? Because customers balk. Why service is less for n equal to 1? Because there is only one customer. So, these must be remembered. So, what we do again, by similar way we find out the equations. How do we find the equations? Look here at node 0, 2 P2, that is in 2p1 equal to 1p0, that goes out. At 1, what is in? 1p0 plus 4p2 equal to 2p1 plus 1p1 equal to 3p1. Similarly, at node 2, 1p1 plus 4p3 equal to 5p2, and at node 3 we have what is in is 1p2, what is out? 4p3, and p0 plus p1 plus p2 plus p3 equal to 1. So, these are all the equations that we need to write, and once we write all those equations, then we can solve like we solved in our previous case, obviously using out of 4 maybe 3 equations and the final equations, and then after finding each probability in terms of p0, when you solve them all, then you may find p0 is 32 by 53, p1 16 by 53, p2 4 by 53, and p3 1 by 53. Now, once we find out all the probabilities, now let us try to get the answers. What is the probability that a caller gets to talk immediately? If these are my 4 probabilities, when a caller gets to talk immediately, after either the system is free or there is only one, is it not? The caller will gets to talk immediately if at least one of the 2 phones are available. That means that probability should be p0 plus p1. What is that probability? 32 by 53 plus 16 by 53 equal to 48 by 53. What is the probability that caller will be put on hold? That means both the phones are busy, but the hold facility is available. When that can happen? When we have the probability of p2, means there are only 2 2 people in the system. So, that probability will be p2, but is 4 by 53, and when the caller will get a busy signal, that is p3, because probability more than this, because there cannot be any other system state, because rest of the customers balk, that is 1 by 53, and the same is shown here in the result. Caller gets to talk immediately, p0 plus p1, that is 48 by 53. Caller will be put to hold, p2 is 4 by 53. Caller gets a busy signal, 1 by 53, right. So, these are the details of the finite queue space model. Next one which we need to discuss further, that is called the queuing cost models, right. The queuing cost models essentially talks about the there are 2 types of costs that are involved in a queuing model. What are they? Service cost, cost of service, and the other is an waiting cost, because the customers are waiting. So, a trade off is necessary. Why? Because if more customers are waiting, waiting cost is more. What we tend to do? We tend to give better supply, a better service. As we try to give better service, the waiting cost will go down. People wait less and less, but service cost will go up. So, you see total cost, which is service cost plus waiting cost for the station, is going to go up if the service cost is too high or waiting cost is too high. That is where a trade off is necessary, and the queuing cost models really tries to achieve this kind of trade off. Let us discuss this in our next class. So, thank you very much.